Thanks everyone for coming. It's great to have so many people here who want to potentially hear about some aspects of my research. I chose to talk about this topic because it's very local to Berkeley. So this was kind of, at least for me, coming from the theory side, like a big collaboration. So we were 6 people, plus a lot of people from the experimental side involved in this. And so I think this was a pretty cool program we had here. And also, I will show that later. There are a lot of people involved. If you're interested in doing any aspects of the things I talk about, reach out to them. They are all typically happy to have undergrads working with them. Some of them are up at LBL, so it might be a little bit harder, but LBL also has a lot of summer programs. So if you're interested in doing research there, reach out and keep tuned, I guess. So when I was asked for a title for this lecture, I called it Finding Dark Matter, the Future Plasma Wakefield Collider. But what I really want to talk about today, and it is basically answering 2 questions. One is, yay, that just worked, and now it doesn't. Sorry, let me try that again. Well, sorry. Okay, don't know what happened. So this is the first question I want to answer today, which is why are particle physicists obsessed with dark matter? And I mean, I guess it's not only particle physicists, dark matter also shows up in a lot of pop science and so on. So maybe the right question is, why is everyone obsessed with dark matter? And then the other one, it just switched slide beforehand, right?
Did you click on it and then press the key? If you click on it sometimes, it works.
Thanks. This is a new slide, no? Sorry. So the other question I want to answer that is close to my research is why do particle physicists build particle colliders, which sounds like maybe very obvious, but these machines cost a lot of money. So this is like a question we get asked a lot. Why should we build a new collider? And so this is kind of the 2 things I will talk about in like the first part of this talk, and then I want to give you a very concrete example why I think both of these topics are very connected and very cool. Okay, and this is the promised list of names. So the people I work with are these people who all have been or are at Berkeley. If you're looking for research opportunities, Simon is the guy to talk to. If you're more interested in like the experimental sides, these are our friends from Atlas. Atlas is one of the big experiments at the LHC. You might have heard of it. And so the guy to ask about research was Simona. And then these are my new friends from the Accelerator Technology and Applied Physics Division, which do plasma physics, but also work at the Bella experiment and laser physics, like up at the lab. So pretty much, if you're interested in plasma physics, reach out to any of these people. They are all very welcoming. Okay, with that, maybe let me answer the first question I put up there is why do we want to build particle colliders? And I want to start off by showing you this very beautiful figure, which is a standard model of particle physics today. And it doesn't really matter what's in there. I mean, these are the particles. Everything that exists is made up of these particles. And if you look at this, it looks like very complete. I mean, this is a beautiful design. But I mean, this is not complete. We know that. And we'll talk about that a little bit more later. The way why it looks complete is because I designed this figure to look complete. Like there's nothing missing there. If you go back 100 years, I could make this very complete looking figure But no, there's a lot less particles in there, right? So these are actually particles you probably all know. So we have the photon, which is usually depicted by gamma. We have the neutron up here, the proton, and then the electron. That is all the particles that were known and observed 100 years ago. And so what happened to get from this to this was a lot of smart people made observations and discovered new particles. And one of the most successful way of discovering these new particles is by particle colliders. And that basically, particle collider, what they do is they accelerate particles as fast as they can and then collide them together. So you can think of that like if you take two eggs and smash them together, you get to see what's inside, right? And so if we smash protons together, for example, we get to see what's in. And so I think you are all old enough to maybe remember the discovery of the Higgs boson in 2012. That was my last year of high school, and this is what basically caused me to become a particle physicist. But you can also see like in green, like some other particles that have been discovered at particle colliders. And in fact, particle colliders have been the most successful way of how we have discovered particles. So if I claim this figure is not complete, what I want to have is a particle collider to find out the missing parts of that. And one of the missing parts is dark matter, which is the other big thing I will talk about today. The reason why I know dark matter exists, if we think in a very simple picture and take all the particles we know, we put them up really good, we should get our universe. In fact, we don't get our universe. What we get is like this tiny slice of 5% of visible matter that we understand. But there is more to the universe. There's amount in dark matter, which makes up 5%. And there's dark energy, which I won't talk about today, but it's basically the largest thing in the universe that causes the expansion of the universe to be accelerated. So basically, this beautiful figure that I in the beginning claimed might be complete gives us 5% of our knowledge, which is, in my perspective, very little. And so I want to find out what the remainder is. So what is dark matter and dark energy? Well, I don't know, and no one else knows. But we have some ideas. I will focus on the dark matter side, as I said, and not on the dark energy side. But feel free to reach out to any of the people I showed up in the beginning to talk about any of these two topics. When I say we know we have dark matter, I say that because we have a lot of evidence for dark matter. And I don't ask you to understand all of that. I just wanted to show a bunch of pretty pictures of evidence for dark matter. But I want to very briefly focus on rotation first, because this is something we can actually understand just based on like high school physics. And that's very cool, I think. So if we have a galaxy, we have some mass in the middle, and we have a lot of stars kind of circling around that. So these stars will experience two forces. They will have a gravitational force between the mass in the center and their own mass, and then they will have a centripetal force, which everything you swing around in a circle will experience. And so you can write these two forces down like this. You've all done that before. And then solve that for the velocity, which I just did for you, but I'm sure all of you could do this. And so then we can measure the velocities of the stars, and we would expect, as we go further out with the radius here from the center, we would see a 1/square root of r proof, which would look like this, or like this dash line. What we actually observe are like the yellow dots right here and the blue dots right here, which looks very different from the dashed line we would expect just based on our knowledge of physics. So if you look again at what we have in the velocity distribution, we have the radius, so the distance from the center, that's fixed, that we know just for this parameter. We have the mass, also fixed. We don't know. So we assume that at the mass, that makes a difference. G is just a constant that you know again from high school physics, or 1 or whatever. So we know the only thing we can vary is the mass, and so we assume we need more mass in the universe. We have this line that fits actually the data. And so since we can't see this mass, we can only see the visible mass, we call it dark matter. Very cryptic, I know. I said we have some ideas what this mass could be, and by some ideas, I mean a lot of ideas because we have literally zero clue what it could be. So this is kind of the theorist's perspective of dark matter. This is just different kind of classes of ideas, and all of them have different subclasses of ideas, and all of them have hundreds of papers written about them, and still we haven't found dark matter. That is not for the lack of trying. And I will talk about how we try to detect dark matter in a moment, but I want to focus on one specific idea for dark matter and all of that, and that is what we call the Higgsino. So I apologize, the slide is a little bit technical. It's not super important to get the details. What is important is we have a particle that reacts to the standard model to like the circle I showed before that we call dark matter. And the look particle has two components. One is charged, one is neutral, and that is similar to this kind of Higgs boson thing that I talked about earlier. There are some differences between them and their quantum numbers that are not super important for us. What is important for us, this neutral component with 0 here, would be dark matter. The charged one is very nice because that's something we can observe in experiments. And so for me, something that I can observe is useful. Something I can't observe, well, we will never know about it. So then we need to get dark matter in the universe, right? And so this is happening through a process that we call freeze out, which I think is a very standard kind of scenario in dark matter physics. And it's relatively easy to understand. When we assume that early in the universe, after the Big Bang, there's a lot of dark matter and there's a lot of standard model particles. They can interact with each other. Dark matter particles can become standard model particles. Standard model particles can become dark matter particles. This is kind of what we call thermal equilibrium. And so on my little timeline of dark matter throughout the universe, we are up here where we have a lot of dark matter. What happens next is that the universe expands and cools down, and that leads to standard model particles no longer being able to produce dark matter particles. So on this arrow here, we would lose one direction. So everything only now goes this way. But now that we have dark matter particles producing standard model particles, but not the other way around, we lose dark matter particles in our universe, right? So we have less dark matter in the universe. What happens next is the universe gets even bigger, it pulls even more down, and at some point dark matter particles don't get close enough, often enough to produce standard model particles, because the universe is so big. And so that means this arrow completely goes away, we don't have interaction between the two sectors anymore, and the amount of dark matter becomes constant again, and this is the amount of dark matter that we observe. So whenever we have a dark matter scenario, we want to have some kind of interaction that allows us to produce exactly this figure. There's a fun thing that happens specifically for this particle, the Higgsino that I mentioned, and that is called the WIMP miracle, something you might have heard of before. This process of dark matter and standard model particles interacting depends on two parameters only: the mass of the dark matter particle and the strength with which they can interact. And so if you put in for that standard model like values for the weak force, which is electrons interacting with each other, basically, you exactly get that we get out the right amount of dark matter in the universe. So that's kind of a fun coincidence, and people call that WIMP miracle because WIMP is kind of this class of dark matter particles, the Higgsino force. And so a lot of people are very fascinated with this Higgsino because it has this fun coincidence, this like miracle thing. And so because of that, we have spent a lot of time searching for this Higgs particle. And typically in dark matter physics, we think of three ways of searching for dark matter particles. And so the main most standard way is through direct detection, where we assume a standard dark matter particle flies into our detector, hits a standard model particle, and then they bounce off each other like billiard balls, for example. A standard model particle then has more energy than before because it was hit by the dark matter particle, and detectors can measure that. In fact, here at Berkeley, we have an experiment that is called Zeppelin, that is doing exactly that. So there's a big tank of xenon that hopes that a dark matter particle will fly in and excite some of that xenon. So far, that has not happened, but maybe it will. Another way to search for dark matters, so-called indirect detection measures. The idea here is that dark matter particles by chance come close to each other and create standard model particles, most likely photons, so light. And this light can be observed by different telescopes. This one is a telescope that is called Cherenkov Telescope Array Observatory. That is one of our best chances actually to see the Higgs, so very fascinating. And the last way is colliders, and I already told you that I love colliders. So the idea there is that at very high energies, very fast particles collide and potentially can produce dark matter candidates. For the Higgs specifically, all these searches have been done, and I'm trying to show you some results. So here we have on the x-axis the mass of the Higgs, and then on the y-axis we have how likely it is to happen. The Higgs is down here. Listen to the word. Our experiments are this green line, and so you can go see this is like 2 orders of magnitude slower. The other thing you can do is there's something written here that is called the neutrino. And this is a big problem for direct detection experiments, because in this region that is called neutrino flow and neutrino fog, the detectors use a lot of neutrinos and can't distinguish them from dark matter. So basically, everywhere on this neutrino flow, we can't actually use this method to detect dark matter. So that's very sad for our Higgs, because direct detection won't be able to see it with the methods we use them. But maybe one of you will come up with a better method at some point, and we'll find the Higgs. At colliders, things work a little bit different. Again, standard model particles collide, dark matter particle flies out. Unfortunately, our detectors at a collider can't actually see dark matter particles. So how do you make them visible? How can you still see them? And that needs 2 ingredients that are also very easy to understand. One is an additional standard model particle, this is this kind of third leg here. And the second is momentum conservation, which you all know about. The momentum of the 2 ingoing particles should equal the momentum of the 2 outgoing particles. If I measure the momentum of this and this particle, I know how much momentum these 2 particles would carry. And I tried to make a little video of how that would work. So you have particles flying in, the new ones are produced, and then you measure the momentum. If you have too much momentum on the visible side, you know there has to be some missing momentum of that, and this is dark matter. Again, this is hard because neutrinos are invisible and could also be that missing momentum, but my experimental friends are actually very good at doing these searches. And yeah, you can see that kind of here again, we have the dark matter mass here. And this is kind of the lifetime of the charged particle. It's not so fun. What you can see is what Atlas and Scherb, the big experiments at IHC, have measured, and you can see they kind of exclude the xenon masses up to 200-ish GeV. That's pretty good. What we would want to see is excluding or discovering at 1.1-ish TeV, so basically an order of magnitude higher. So a little bit similar to the direct detection, and LHC might have this evolution to discover the Higgs. So that leaves us with like the third method, which is the indirect version, where dark matter produces photons that are observed by some telescope. And this is a plot made by some of my friends up at the lab for the specific telescope I showed you earlier. And the wish basically shows the timeline on the x-axis of a potential discovery. And so in physics, we often say that we need 5 sigma for discovery. We might have got that. I want you to focus on the gray lines. The orange are a little bit too optimistic. And you can read for different ideas about the astrophysics of dark matter. This particle could be detected roughly in the 2030s, which is actually very, very cool and very exciting. So maybe within the next 10 years, we will find dark matter. And that's great. What's not so great is, if you look at these 3 gray lines, they are very far apart, because there are a lot of uncertainties in astrophysics that we don't know about. So we actually don't know where we would be there, and we also can't really study that particle, because for one, it's an indirect measurement, and for the other, there are all these big uncertainties in there. So what we really would like, if that telescope can find the Higgs, is to have a way to produce it here on Earth. And again, colliders, because colliders are great. Yes.
So are these lines different like galaxy shapes?
Yes. Yes. It's the shapes of the dark matter halo around the galaxy.
Okay.
Yeah. Great question. Yeah, feel free to ask questions at any time. I probably should have said that in the beginning. And so to be able to see the Higgs and produce the Higgs on Earth, we want to have a more powerful collider. And so currently there are 3 main candidates discussed. One is a proton-proton collider, which is similar to the LHC at Scherb, where you accelerate protons to 100 TeV, smash them together, and hope to produce new particles. The reason why we need 100 TeV compared to these other options where we need 10 TeV is because the protons actually work in elementary part. It consists out of quarks and gluons, as shown here. So what actually collides are those quarks. And so if you think there's 3 quarks, total energy is 100 TeV, each of them has roughly the graph of that. And this is how we get our 10 TeV. Center of mass energy. When I say 10 TeV, that maybe sounds like a weird number. TeV stands for tera electron volt, which still doesn't sound very great. But luckily, CERN helped me out and found this very nice analogy. So 1 TeV is roughly the energy a mosquito has when it flaps its wing. Now, a mosquito is small, but protons are much, much smaller. So they are million times smaller than a mosquito. So you imagine this kinetic energy of that mosquito all condensed into 1 proton and then multiplied by 100. And this is how much energy these protons have roughly. Or multiply them by 10 if you want to collide muons, which are elementary particles, or electrons, positrons, or photons, again, elementary particles. All of these options are great. I'm a fan of all of them, but they cost a lot of money, and we will be lucky if even one of them is built. One of them will be built. Let's not be too pessimistic. I want to talk about the third option here, and I want to talk about a specific case of where we use a very unique technique to accelerate the electrons and positrons in this collider, which is called a plasma Wakefield collider. The way that works, I tried to find a little analogy, and I have here this nice picture of the guys sitting behind a boat in the boat's wake. So if you imagine the water is plasma, which is basically just ionized electrons and ions. And you drive with the boat, and so I call it driver beam because it drives. through the water, it will leave this wake. You all have seen that before. On this wake, you can surf because the wave has some gravitational potential. And so the surfer, which is my electron, can accelerate on this wave. Now, if we put that into particle physics terms, what we have is a plasma where we shoot a driver beam through, which is either a laser or an electron beam. The electron beam will create a wave similar to the probe, so it will push basically the electrons in the plasma to the side. This doesn't create a gravitational potential, but an electrical potential. So this is shown by this little key here. And then you can use this electrical potential, this electrical field, to accelerate other electrons with it, which would be the surfer in this kind of picture. Our friends up at the lab are very good at simulating and creating these processes. So if that is something you care about, go talk to them. So I talked about the surfer as an electron, and that is for a reason. We don't know how to create a positron plasma. We don't really know how to accelerate positrons in an electron plasma. And so as a theorist, we heard that positrons are so much harder to do in plasma Wakefield colliders. And so we asked ourselves, can we find this Higgsino even if we use only electrons or only photons in the collider? The other thing that happens in these colliders, sorry, this is another very technical slide, is actually a very fun thing. So this is not to scale, but maybe to give you an idea. At the LHC, the current particle collider we have, the bunches of protons that are collided are roughly the size of like millimeters. At a plasma Wakefield collider, the bunches that we will collide that are packed very tightly with electrons are ordered micrometer to nanometers, with this many, many orders of magnitude smaller. What happens if you put a lot of charge in a small region and then move it is you create large electric and magnetic fields. You have Lambda in your temperatures. I try to show that a little bit here. So this is our large amounts of charge. And so what happens if you have strong electric magnetic field is that the electrons can spontaneously radiate off a photon, and these photons spontaneously can create electron-electron pairs. And so what happens is, even though I start out accelerating an electron bunch, what I will have at the collision point is an admixture of electrons, positrons, and photons into that bunch. And for a long time, this has been considered a big, big problem because you want as many electrons collisions and not some positrons and photons in there. And so the way people try to reduce this effect is by shaping the beam in different forms. So if you would cut this bunch in half here, you can have either round beams where it's round as a base face, or you can try to squeeze the beams together where you get like this concavity flat beam shape. This flat beam shape has less of these magnetic fields, so you have less photons and other stuff in your beam. This will give you a cleaner beam. There's a problem with that. Experimentally creating these flat beams is incredibly hard. Don't ask me why, I'm a theorist. So if that is super hard, the question is, well, maybe we can use that additional photons and positrons in the beam. And so I wouldn't be talking about that if the answer wasn't yes. So the answer is yes, we can use that. And I want to show you a very specific example of where that can actually happen the way we would expect. So this is an example of these collider searches, as I talked earlier, and specifically in one of them. So what we think is, again, on this side, we collide whatever standard of particles with our case electron and positrons, or electrons and electrons, or electron and proton, or proton and proton. These kind of conditions should happen. And we want to have two Higgsino's coming out, as well as a proton. And so we look at different scenarios. So we look at the case where we have E plus and E minus in the original beams with the round and flat profiles. We look the same for the E minus case because that's easier to accelerate. Again, for the rounded flat beams. And then we also look at photon. The way we get photon is we accelerate an electron beam. We shoot a laser onto the electron beam. That causes photons to be scattered off of that electron beam, and we get a bunch of high energy photons out of that. So this is kind of the idea. The most efficient way of producing this process, where we have the hyperparticle and the standard model particle, with these kind of initial particles, is actually using the electron and photon. And so this is already kind of gives you the answer of why I said beam straddling is useful, because in none of these scenarios, we actually have an electron and a photon originally in your beam. And so one of those would always come from this beam straddle, from these effects where we get this admixture in our beams. And so we did the calculations, we ran a lot of simulations actually. We plugged the cluster at the lab for quite a while to do that. And so what we get out is basically we can find out how often these processes would happen for the Higgsino. And so I show that as a function of the Higgsino mass for different collider types. And I want you to focus only on the two red lines. The darker red line is this round beam profile that I talked about. And the lighter red line is like the smushed flat beam profile. And as particle physicists, we want to produce as many of these new particles as possible. So we want to be as far up in this figure as possible. And so you see the darker red line is higher up, which for me means, well, round beams are actually pretty nice. And this is very exciting to hear from my experimental friends who are like, yes, less hard work. The same you can see for like the orange and lines, which are the E minus collider. You can see in total these lines are a little bit lower. But again, the darker line that is like this round beam is higher up than the flat beam line. So again, if we build an E minus collider, we want round beams. So that makes my experimental friends happy. Finally, you can see the photon line is somewhere in between these. And so if you ask me, well, which is the best option for that, I would tell you, well, it's the round beam E plus E minus collider. Unfortunately, that is hard to build. So the flat beams are, well, I'm kind of advocating here for the photon collider potentially. We can translate that into what we call like discovery plots. So again, we show the mass and we show different collider options here. And so we want to reach this dashed line, which is where we think we see this. You can see the two round beam, the two E plus E minus option both easily reach that line. So flat beams do a little bit, sorry, the E minus do a little bit worse, and the gamma is doing similar to the plus E minus. So if now someone was asking you, well, what should we do? Just based on this one search, that knowing my experimentalist friends really don't want to do the E plus E minus collider, I would tell them, there would be a photon collider, and I would be very happy. This is actually not the full story. I'm lying to you a little bit or simplifying this a little bit. There's not only one way of searching for the Higgsino, and we did kind of different options. So each of these blocks of colorful lines shows a different way of how we could search for the starting collider. But I think the general trend is still that the plus E minus option be great, and the round beams do better than the flat beams, but although the photon collider has a lot of potential. What I should mention here are the two other options that I talked about earlier, which is the linear collider, which is like the first gray line, and then the photon collider, which is the second gray line. And well, for some scenarios, I would say our plasma Wakefield collider idea would do way better than the gray lines, especially for example here. We can do that with photon collider that's very well. In other cases, the photon collider that's amazing, and we can't keep up at all. So you can see this line didn't even sit on the floor, it would go all the way over here, so it would do way better. But overall, I think this shows that this idea that is potentially, it is for sure needing less space and potentially needing less money is a viable option. But all of these different kind of colliders have different strengths and advantages. And so I spend a lot of my time thinking of how we can overcome these kind of challenges. Okay. So with that, I want to kind of answer the two questions I asked in the beginning. Why are particle physicists obsessed with dark matter? And I think this plot shows it very well, just because we don't know what the universe is made of. And as a physicist, that really bugs me a lot. And the other thing is, why do particle physicists like to build particle colliders? Well, it's our best option to observe dark matter, specifically here the Higgsino, but also other dark matter here on Earth, where we are free from any astrophysical uncertainties. And that is very cool, because then maybe instead of 5%, we know about 30% of the universe. That would be a great step forward. So that's all. Thank you. Yes, go ahead.
Why do you think particle colliders are better for action?
Oh, I mean, this is kind of just because at the moment we don't really know how we overcome this neutrino flow limitation. So for this specific, I mean, there are ways we can think of, but they are not being built at the moment, and they are still very much. With the current experiments, there is no chance of seeing the Higgsino, which is potentially the best motivated dark matter candidate we have thought of. And so we are trying to get below this neutrino floor, but it's very hard. And so we can't do that for this specific type of dark matter. I mean, you can see here these people who did this plot look at very different dark matter scenarios as well, and they might be discovered by direct detection. What colliders allow us, in addition to just discovering, is also understanding more about its properties, like about its spin, its potentially charged partners, and so on. And so no matter where it is discovered, I think colliders will allow us to study the most. And I want to know as much as possible about nature. So this is why I like colliders. Yes.
Think of the awful plot. You might tell us, like, when you like started out doing physics, were you always interested in dark matter? Like, what got you interested in this one?
That was a good question. That was kind of an organic process, I think. So I told you in the beginning, when I was in my last year in high school, the Higgs boson was discovered. And I actually lived not too far from CERN, so where that was discovered, only a couple of hours drive. And so my physics class went there to like talk to the people, and that was fantastic. And so I was like, I will become a particle physicist. And then I started doing research, and I first worked on neutrinos, which is also a lot of fun, but it didn't feel quite right to me. And so my second research project as an undergrad was on dark matter. And I was very fascinated by this idea of this thing that's out there, but we don't know about. And then I just stuck with it because it's so fascinating. Yes.
How are you able to make educated guesses about the properties of the Higgsino without it being predicted by the standard model?
Right, we can't. There's one thing we can do, which is using this WIMP miracle kind of thing to see how heavy would that need to be and which thing would that need to have to find the correct amount of dark matter today. And so we choose properties of the Higgsino. Wrong direction. We choose for it to be a particle that is, now I'm going to use very technical terms. I hope that's not super confusing. That is a vacuum, so it has two components, and it is charged under the electroweak symmetry, so it interacts via the electroweak force. And so based on this knowledge of this interaction, we can calculate the mass it would need to have to give us the right amount of dark matter in the universe. And this is so kind of one way of doing it. But when I showed you this figure, I mean, all of those are hypothetical ideas that are very different, and this is because we have no clue. So I mean, there are some symmetries you can think of that are maybe more likely than others, but in general, we are kind of being creative and just figuring out what dark matter could be, and then kind of thinking of all possible scenarios and how they could be discovered, and then trying to hope to discover something. Yes.
Maybe I missed it, but you said you see or expect to see more dark matter particles when you have electron and photons.
Yes. Yes. I mean, this is kind of just a feature of this. We defined our final states on one dark matter particles and the photon or electron here. And so knowing, based on the choice of the Higgsino, we know how it would interact with the standard one. This is something we fixed. And so you can write down all these interactions and you can just calculate which process, which kind of initial state would give you the most particles. And in this case, it's the electron photon initial state. For different dark matter candidates, it would be a different, it's very model specific to some extent.
I'm wondering how photons and photons can collide. It seems that like there's photons everywhere.
Right. I didn't draw a Feynman diagram. For one, these are very high energy photons. But what we think of when we say collision is maybe not as much as the billiard ball example I made, but basically that they interchange force carrier particles. And so I don't know if I should draw. That's a very scary thing to do. So what you can do, maybe let me give you a very easy example, and then go to the photon example. If you collide, right, hold that back. So let's start with an easy example. If you collide an electron and a positron, what happens is not that they bump off each other, but that they exchange other particles. One possible particle is a photon, and since it has so much energy, it can decay, it can produce other particles. Some of them might be the dark matter. Similar, if you now do photon, they don't collide, but they basically exchange one of these electrons, creating very high energy electrons on this side, which then in turn can produce heavier particles. So it's not like this, but it's the exchange of another particle leading to other high energy states. Does that make sense? So it's, each of them is supposed to have 5 TeV. That's tera electron volt, which is again 1 electron volt. No, sorry, I went wrong again. Exactly. Energy of a mosquito in a million times smaller for a proton, and so probably at another million for making it into the photon. So yeah, a lot of energy in very little space. Yes.
So two questions. So for this, the last one that we should talk about the ones.
This one?
So yeah, so I think that's a little lost here. So we were talking about like minus and minus might be better than plus and minus.
Yeah.
Now looking at this plot, it seems to me that E plus minus is still away.
Yes.
So what is the advantage of minus and minus?
The advantage is that it is experimentally a lot easier to accelerate an electron over positron. And so when I showed you this plot, I assume that we can accelerate positrons in the same way as electrons. That is, at this stage, we don't really practically have any proof that we can accelerate positrons with plasma Wakefield colliders. Even if we find that there are a lot of great ideas how to do that, we will probably collide less particles on the positron sides compared to the electron side. So those lines would actually move down in a more realistic scenario. And again, if we can't build that as nice as the lines are, they won't be able to produce them.
So E minus, you get farther up to the right than you can when you plus and minus. It's just that in this, I guess in this particular plot, you don't see that. You don't see that again.
Yeah, I mean, you can, maybe I have a figure for that. No, I don't, not in this talk. Yeah, okay, let's stick with this one for now. So, as we go, so once we have 10 TeV, so we have 10, and we produce 2 of them, we can't actually go further in energy, right? You have 10 TeV in the initial state, you can produce at most 2.5 TeV just by energy conversation. And so what you, instead of, maybe let's go to this, would have if you would imagine the electron beam looking like this, where you have a lot of electrons in there. The positron beam would mean we have half of the little blue dots in there. So we would in total actually produce collide less particles, and so in a real scenario, this realistic one, you would collide less particles, so you would get lower numbers of events, so the red lines would move back while the orange lines stay where they are. And so this is kind of why the red lines are very idealized, and we actually don't think we can choose them. This is kind of why we say electron is potentially the better option. But you can see that the blue line is above the orange one, so that's an even better option, and that is that one we know how to realize. Yes.
You talked a lot about the pros of a Wakefield collider or a Wakefield collider, whatever it is. But what are like some of the cons or drawbacks and that
Yes.
I think is the big ones, like when that immediately pops out is how small they are. Like, yeah, it can get broke, there's no to neutralize it, also like, you know, it's going, you know, accelerating that fast and this small amount of distance can, ask a question for.
That is a great question, and let me answer it in a broader way than you meant it. So all of these options, with the technology we have now, we can't build them. You need to do a lot of research and development, and these are actually things that collect 20%. Yeah. For the proton-proton collider, the main thing is that we decrease on magnets that we have yet. So this would need a lot of work in that magnetics. So if that's what you want to research, I will be very happy. For the muon collider, what is very hard is to focus muons. And so we don't really know how to do that. And so this is where we need to research in that case. For the electron positron or for the plasma Wakefield collider in general, we can accelerate electrons in one plasma cell. So we can create a box of plasma, if you will, and do the acceleration in there. We don't know how to stack the next box in there to get it to even pass the energies to the energies we want. The other part is that once we use the plasma once, it isn't a smooth, nice looking plasma anymore. So stabilizing it after shooting one beam through is another big challenge. So there's a lot of research needed to be done for that as well. Great question.
I'm interested in the space telescope approach to detecting the possible Higgs xenos. Would you mind going in a little bit more detail about what they might be hoping to see there?
Right. So the idea here is that at some point in the galaxy center, dark matter hits each other and produces photons. So this specific telescope I was talking about here is building Cherenkov telescope. So basically photon hitting water and then producing some Cherenkov rings, I guess. And they will have a station both on the northern hemisphere and one on the southern hemisphere, which allows for one larger sky coverage, but also like directional probes, since you can do some triangle. So as far as I know, the northern telescope is already built, or should be finished at some point this year. I'm not completely sure on the timeline. The southern one will then be started to be built once that happens. Once that is online, they will basically just point it in the direction of the galaxy center of the Milky Way and hope to observe something. They don't just look for dark matter, they also look for standard model astrophysical things like gamma ray bursts and whatever might be happening in the center of the galaxy that I don't know. And so once they take data, they will try to analyze it, understand where this comes from, and hopefully what it is. And so based on seeing something or not seeing something, then they will be able to tell us if there's dark matter or not, or what dark matter is. Hope that was somewhat helpful.
No more questions? Well, anyway, thank you so much for coming, guys.